this for Europe's victory.
He's done it.
Europe's hero, Colin Montgomery.
4 more to Flintoff.
Bradley Wiggins, Olympic champion.
Who's going to win the final race of the year? You decide next Sunday. BBC Sports Personality of the Year, including a live vote for the Team of the Year. Next Sunday at 8 on BBC One.
Music, Radio 1 from 7 p.m.
This is the story of how we learned to manipulate light and how light manipulated us. Of how an instrument for sailors rocked the foundations of the church. Of how a micro-world revealed the machinery of creation. And of how telescopes unlocked the secrets of evolution. This is the story of how light changed our world. Light Fantastic continues Wednesday at 9 on BBC 4.
A look to the heavens here on BBC One now with Patrick Moore and the sky at night.
Good evening. When I was young, the biggest telescope in the world was the Mount Wilson 100-inch reflector in a class of its own, and the second largest was the 72-inch Metal Mirrors Ross telescope. Well, things have moved on since then. We had the 200-inch, other large telescopes, and now the largest and most powerful telescope in the world is the VLT, or Very Large Telescope, made up really of 4 and 8-meter mirror working together in the best possible site in the Atacama Desert of northern Chile. Well, some years ago, I went there, we did a sky at night from there, and the telescope was being built. Now it's complete, and Chris Lintott has just been there.
I'm standing on the summit of Paranal, and behind me are the 4 domes which house the telescopes that make up the VLT. Each one of them would be a world-class observatory in its own right, but the plan here is to get them to work together, and when that's achieved, we'll have an instrument theoretically capable of seeing a man on the surface of the moon. The site at Paranal in Chile is ideal for astronomy. Rain is extremely rare, and the whole atmosphere is almost completely dry. Not the ideal climate for wildlife, but as we're in the middle of the Atacama Desert, the driest anywhere in the world, literally nothing lives here except the astronomers. Difficult though it is to believe, this is an ancient seabed which has been pushed upwards by the process of continental drift. It bears a striking resemblance to the surface of Mars, as seen in pictures sent back from spacecraft like Mars Express. Red sandy soil, boulders, even the occasional dust devil. I half expect to see the rovers Spirit and Opportunity come rolling over the nearest hill. The unique climate of this place is easily seen in satellite images. Air, cooled by the Pacific currents, forms an almost permanent cloud cover at sea level, whereas further inland, over the Chilean Andes, the air is cooled enough to form cloud. In the middle, we have perfectly clear nights, 350 days a year.
We astronomers always want to do things better, to go deeper, to look for fainter objects. So when we were satisfied that we had a very good observatory on La Silla, we decided what's the next step, and the next step was to go bigger, and going bigger was the VLT. And the VLT was a major investment for ESO, and in order to maximize the return, we wanted to put it in the best site, and we finally determined that this place was the best for our needs.
So what have been the scientific highlights for you?
Well, there have been a lot of scientific highlights. This wonderful facility has provided us with a lot of new results and very exciting ones. One of those results is definitely, which is very spectacular, is the black hole at the center of the galaxy. We have observed the motions of the stars around this black hole. Stars are moving from day to day, really, and we could determine accurately the mass of the black hole this distance. And on top of this, we have observed infrared flares from the black hole, which is something that had never been observed before, and which gives us access to a whole new physics. We've also possibly detected a new exoplanet around another star. And so far we have an image and a spectrum which apparently are consistent with the presence of a planet around the other star. We've been observing with incredible details the surface of satellites in the solar system, Titan for instance. And this is also very useful for the people who prepare space missions to those objects.
As you might expect from an area with skies as clear and as dark as those we have here, there's a strong tradition of astronomy among the indigenous people of Chile. In order to recognise these traditions, the 4 telescopes that make up the VLT take their names from those of astronomical objects in the Mapudungun language. And so behind me is Antu, which means the sun, Koyan, which means the moon, Melapal, which means the Southern Cross, the most famous of all the southern constellations, and then Yepan, which translates as the brightest star in the sky. What we don't know is whether they've noticed Venus moving against the background stars, and so we don't know whether they counted Venus or Sirius as the brightest in the sky. Yepan was the last of the 4 telescopes to be brought into full service, and once the enormous dome doors are open, light passes in, reflects off the 8.2 metre diameter primary mirror, goes upwards before hitting the secondary, and then coming back down either to an instrument underneath the main focus or into the giant cameras on either side of the main telescope. Now, although the VLT mirrors are the largest ever built for astronomy, they're very thin, only 18 centimetres. So as the telescope looks down towards the horizon, the perfect shape of the mirror will deform under the effects of gravity. However, because the mirror is thin, actuators and computers underneath the telescope are able to adjust that shape, and so the mirror retains its perfect form wherever the telescope is looking. Even on a site as good as Paranal, and with all this technology, we still have the fundamental problem that the telescope must look through the Earth's atmosphere, and it's the shimmering of that atmosphere that causes stars to twinkle, and which affects the precise measurements scientists use the VLT for. Now, using what's called an adaptive optics system, a moving mirror is able to compensate for this atmospheric movement. If you like, the telescope's been fitted with glasses, and the VLT is one of the first telescopes in the world to regularly employ this new technology.
This is a quite new system which was installed in 2001, which is able to correct the atmospheric turbulences. The light first goes on a so-called wavefront sensor, which is also a camera which analyzes the images for distortions. And from this information, a very fast computer is calculating the correction for a deformable mirror, which is a soft mirror with 162 actuators, which is able to correct the image to get a straight one.
I mean, looking through a small telescope, you see the atmosphere moving very quickly. So how fast does your mirror have to move to compensate?
Well, the system is able to correct up to 500 times per second.
Well, it's impressive. Up in the control room, we have a recent example of Yepan's adaptive optics systems in action. The original image shows stars, but they're blurred. Apply the adaptive optics, and not only do the images become sharper, but you see all the faint objects in the background of the field of view. Each of the 4 telescopes is already in great demand from astronomers, but the VLT was the first major optical observatory to be built with interferometry in mind from the beginning, and progress is already being made towards combining the light from the 4 giant telescopes. Light from each and every telescope involved must have travelled exactly the same distance by the time it arrives to be combined. That means diverting light into loops in order to delay it, and the length of those loops must be controlled with incredible accuracy, which is what makes optical interferometry quite so difficult. I know the 4 telescopes are working individually and working very well, but you have begun to combine their light.
Yes, well, actually a lot. So already 2 years ago we started with 2 telescopes, combining them. We have currently something like 3-4 nights a month when we use at least 2 telescopes together. We have had, as always, a lot of things to learn. It gets very complicated because these big telescopes need adaptive optics. Also, adaptive optics is a new technology.
Right.
This is working well now. Actually, when we operate with 2 unit telescopes together, it's something like 40-50 computers involved.
Wow.
It's a lot of things which has to work at the same time, and if one single piece breaks down, the whole system breaks down.
Within a year, the 4 main telescopes will be joined by 4 auxiliary telescopes, like the one in the small dome behind me. They're smaller, but they're able to move across the entire platform to any of the observing locations marked by these white covers. Here, the light will pass down into an optical laboratory where it will be combined with light from the main telescopes. Due to this complexity and the sheer scale of the project, it could be up to 5 years until all 8 telescopes are able to work together. But the scientific gains from the ability to see the universe's finest details make it worth the wait. Of course, even with the best telescope in the world, you need good instruments to get results. Spectrographs, like Symphony here, split the light into its constituent wavelengths, enabling astronomers to calculate the chemical composition of the objects we're looking at, and via the redshift, their distance. We use cameras as well, based on the same technology as that in your digital camera.
The red one is the infrared camera Konica, which, because it's working in the infrared, needs a very cold detector temperature, which is reached by a helium compressor to 22 Kelvin.
That's cold. And of course, on this telescope, Jeppen, we've got one of the newest instruments up on the mountain, which is Symphony. And the exciting thing about Symphony is that it can take spectra across a whole field of view.
Yes, correct. It is only a spectrometer. You can do a like 3-dimensional image in one shot, because it analyzes every object with respect to a spectrum.
You pick up a redshift, so you have a distance. So
yes.
I guess it's the first 3-dimensional astronomical camera.
Yeah, you can say this.
It's sunset, but before the observations can begin, the engineers must get the telescope ready. The light fades very quickly when you're as close to the equator as we are here, but the half an hour or so of twilight we do get is a very busy time up on the mountain. First, the telescope tilts over onto its side, simply to avoid anything falling on it when the doors are opened. It weighs over 400 tons, and it's an incredible sight to be inside the dome watching it move around. Next, the doors themselves open, opening the telescope up to the sky, and then the shutters along the front, which provide shelter from the wind during the night, open one by one. Around the rest of the dome, holes open which allow air to flow freely through the dome and across the telescope. When the night's calm, like tonight, the telescope's surprisingly open to the air, and it's the wind blowing through that not only cleans the mirror, but keeps the seeing absolutely steady. The observers that are involved in tonight's programmes will have applied months ago for their time on the telescopes. The VLT is hugely oversubscribed, so it's important to make the most of every second of darkness. The technology and engineering may be impressive, but it's the science that's the really exciting part.
And that is the VLT, so far in a class of its own and providing fundamental results. So time now, I think, to talk to the people who've actually been using it. So I'd say welcome Dr. Isabel Hook from Oxford, Professor Jerry Gilmore from Cambridge, and Dr. Alan Fitzsimmons from Queen's University, Belfast. And all of you have been using the telescope for your different researches. So can I come first to you, Alan, because you've been studying asteroids and you're close to home, so what exactly is your work with the VLT?
Well, what we've been very interested in is studying precise detail the physical characteristics of asteroids in our own solar system. And in particular with the VLT, we've been interested in a theoretical experiment or a theoretical calculation, which implies that as asteroids rotate and they absorb sunlight and re-emit that sunlight as heat, that very act can actually change how fast they're rotating. And this is important for us because we see, first of all, a lot of asteroids that are rotating very slowly. We see asteroids that are rotating so fast they're on the verge of breaking up into small
But you're dealing, are you not, with the, what they call the near-Earth asteroids, those that leave the main asteroid zone and swing very close to the Earth. And these are tiny things, often less than a mile across.
That's right. In fact, the specific asteroid we've been studying is one called 2000 PH5. Now, this is only about 150 metres across, so it's actually quite small, but it does approach the Earth about once a year in July. And when it does so, actually, it's about 15th or 16th magnitude and has actually been observed by amateur astronomers. But within a couple of months, it sinks down to fainter than 21st or 22nd magnitude, and that's why we need the VLT to study it.
What exactly are you trying to find out?
Well, what we want to do is measure its rotation rate very accurately from year to year and see whether or not this theoretical effect of changing the rotation of the asteroid actually occurs. Now, to do that, we've got to measure it very precisely. In fact, we have to measure how fast the asteroid is spinning to better than a millisecond. What we see here is a movie made from the individual images obtained with the VLT of the asteroid 2000 PH5 over a period of just under 2 hours. But if you look at it more closely, one can see it getting brighter and getting dimmer on a regular basis. And this is caused by the asteroid reflecting more or less sunlight as it spins.
If we saw one coming towards us, what could we do about it? Anything?
Well, the first thing we could do is make sure we've got the calculations right, make sure we've got the orbit as accurately as possible. And that's something that's ongoing with all 3,000 near-Earth asteroids that we know of to date. But unfortunately, at the moment, if we spot one coming towards us or on a collision course, then at the moment we have no deflection mechanism in place. Saying that, we would normally have about 10 or 20 years warning. And right now, the European Space Agency is looking at possible missions to try and deflect an asteroid. So we have some time yet.
Well, it's fascinating work, and of course, quite near home. You, Jerry, of course, you're looking much further into the universe.
I had the privilege of having the first British run on the VLT, and it's part of a project that we've been doing for a very long time now, which is weighing things. We've known now for nearly 20 years that the universe isn't made of what we see. The stuff we see is almost irrelevant. It's important to us because we're made of it, but it's pretty well uninteresting as far as the universe is concerned. Most of reality is some completely different form of matter, what we call cold dark matter.
What is it?
Well, that's what we're trying to find out, you see. That's the challenge. So we've been working for many years with the available best 4-metre telescopes, particularly the William Herschel telescope in La Palma, and we've pushed that to its limits, and then we were ready to take the next step, and so that's where the VLT comes in. What we're trying to do, really, is measure how cold is cold. How cold is cold dark matter? And we do this by weighing things. And weighing things is easy. You know how to weigh things. Everybody knows how to weigh things. Essentially, we just measure how fast things are moving. And we know if stars are moving very fast, a lot of weight to hold it back. Otherwise, it will fly away. If stars are moving very slowly, it doesn't take much weight to hold it back. So if I find a little galaxy or a part of a galaxy in which the stars are moving all very slowly, I know that bit doesn't weigh very much. Similarly, if I find a part of a galaxy or a whole galaxy where the stars are moving really fast, then I know that thing weighs a lot. And so by comparing how fast the stars are moving and how much weight that Newton's laws then tell me the galaxy has, with all the stuff I can see, I can work out how much real stuff is there, how much weight is there, and that's the matter.
Which galaxies are you studying particularly? Which types of galaxies?
Well, it turns out that the key to measuring how cold is to find the smallest thing that's got dark matter in it. So we know the universe is full of the stuff. Big clusters of galaxies are totally dominated by it. Even middle-sized galaxies like the Milky Way, we now know, are totally dominated by it. We also know that things like globular clusters of stars don't have any dark matter in them at all. So something in between is where we first find that stuff. And we're fortunate that there are, in fact, the 7 dwarfs. Actually, that's a slight cheat because we found a new one in the course of this program, so there are now 8 dwarfs. But there are 7 and a bit dwarfs, dwarf galaxies orbiting around our own Milky Way, like moons around the Milky Way. And these things have just a small number of stars in them. They're very hard to see. In fact, they're visually under-spectacular, say the least. You can really have to struggle to find them. But it turns out that these things are almost pure pieces of dark matter. So there's these little stars are whizzing around nearly 100 times faster than they ought to be moving, and they make these little galaxies. So these galaxies are the pieces of dark matter that exist in the universe that we can find only because there are a tiny few stars in them. So what we're doing is measuring how fast these stars are moving and how they're spread out. And from that we can just weigh the stuff. And it turns out in these little galaxies that there's about 300 times as much of this exotic stuff as there is of ordinary matter, the stuff that makes up stars. And so this is our best place for finding out the first thing we want to know about what it is, which is how cold is cold. And we think we're getting there. And what are the conclusions you've come to so far? Well, this is all very new, actually. It's exciting stuff. This is almost a press release here. The amazing thing, we've now done 5 of the 7 of these galaxies, and Fortunately for us, they're all very similar. If we got 5 different answers, that would tell us nothing. That would mean that they've all had complicated histories and we still have a real problem. But all 5 of them look the same, and we'll know about the other 2 pretty soon too, in about 2 weeks' time, I hope. And all 5 look the same. In fact, what we see is that the distribution of dark matter in the central regions is really rather smooth. Now, if the dark matter were very cold, it would all fall into the middle. And because the particles aren't moving very far, they just stay in the middle. And so cold stuff would form a real spike, a really dense little centre. Hot stuff, very hot stuff, would be very spread out, like the Earth's atmosphere, you know, spread out over kilometres. And in between would be in between. And what we see is in between. And that's really exciting. So we seem to see this stuff spread out characteristically on a scale of about 1,000 light years. Equivalently, I can say that corresponds to a density of about equivalent to 1 hydrogen atom per cubic centimetre. So it's pretty sparse, it's a pretty high vacuum, but in every centimetre in this room there'll be 1 of these particles in it. So they're there, and that means we can start to find them. And also, if I were to convert this into a temperature, the temperature is about 10,000 degrees. So it's not cold by any means, but it's tepid. So the stuff's tepid. And we are, just for the first time, beginning to find out enough to start to say what this stuff might be. And first of all, of course, what it isn't. So we can cross a whole lot of obvious targets off the list.
Well, Isabel, your research takes you even further, doesn't it?
It does. We're doing a project to study the universe itself and its expansion rate. And about 6 years ago, our team and another independent team found a very surprising result, that the universe isn't just expanding, but it's actually accelerating.
Accelerating the universe.
Yes. And because that was rather a surprise at the time, we've been now embarking on a large project to try and confirm this result and really understand it. So we're doing a project which involves studying distant supernova explosions. And in particular, we're interested in type 1a supernovae, which are so-called standard candles, which means we know their intrinsic luminosity. And that means that if we observe their brightness on the sky, that gives us a measure of their distance.
What's the cause of type 1a supernova? Collapse of a very massive star, or the destruction of a white dwarf?
We think it's destruction of a white dwarf that's reached the Chandrasekhar mass limit from accretion from another companion star, and that tips it over the edge and causes it to explode. So we believe that they always explode with roughly the same mass, and that means that they have roughly the same luminosity when they explode, and that's what makes them standard candles.
How far out can you go?
Well, at the moment we're able to observe supernovae out to, in terms of redshift, out to about a redshift of 1.5, which corresponds to about a time when the universe was about 1/3 of its current age. So we're able to look right back across the history of the universe. And what we do is we measure the brightness of the supernova, which tells us the distance, and we also measure its redshift, which tells us how much the universe has expanded since the light left the supernova. And if you combine those 2 things with a series of supernovae at increasing distances, you actually get a sort of map of the expansion history of the universe. And that's how we're able to trace whether the expansion is going steadily or accelerating, as we believe it is now.
When I was born, we didn't even know the universe was expanding. It was before Hubble proved it, which was a long time ago now. And we've certainly come a long way, haven't we, since then?
Well, that's right. There are so many things that the advance of telescopes has allowed us to discover about the universe over the years and over the decades. And so, for example, if we go back to asteroids, if we look at most asteroids were thought of as being lying between Mars and Jupiter in the asteroid belt, and there was 1, maybe 2 objects that were known to orbit around the inner planets, and now we know of over 3,000. In fact, we regard this as a natural state of affairs, that objects are thrown out of the asteroid belt and in towards the sun.
I wonder what we're going to find. One point about the VLT is that from its site in Chile, you have access to the southern sky, and some of the most interesting objects are in the far south, so from England they are inaccessible. Well, Chris has been there, and he's had time to look round the wonders of the far southern sky.
It's nearly nightfall, and the sun's setting over the desert behind me as the professional astronomers up at the VLT are settling down in front of their computers for a night's observing. But what really excites me on this trip is the chance to see the sky for the first time from south of the equator at this superb site. We're looking forward to sights such as Orion seen overhead, beautiful views of Saturn, and deep sky objects like Omega Centauri, and the Large Magellanic Cloud that we never get to see from the UK. It's going to be a stunning night. And with me are some of the world's leading astrophotographers. Damien Peach from the UK is responsible for some of the most stunning images of the planets I've ever seen. And for local knowledge, with me is Belgian astronomer Daniel Versace, who's lived in Chile for more than 5 years. We've chosen a site just 100 metres below the VLT, and coincidentally, it's the site for ESO's newest telescope, VISTA. When completed, it will be the largest telescope anywhere in the world dedicated to large-scale surveys of the night sky, in this case, both in the optical and the near-infrared regions of the spectrum. We're trying to do as much of the setting up as possible during daylight hours, because here, literally within sight of the VLT, restrictions on light are incredibly tight. In fact, it's rare for anyone to be allowed to bring telescopes up here, so it's a real privilege for us this evening. Daniel, of course, has driven up from the south of the country, but Damien's managed to pack a surprising amount of kit into his airline luggage. So Damien, you brought your telescope out from England despite the excess baggage, but you've had to make some adjustments to it.
That's right, Chris. The polar axis actually needs adjusting because we're much closer to the equator here at Paranal. We're at the poles of the Earth. The polar axis of the telescope would be pointing directly at the zenith, and it will actually track the sky around in a circle. As you move further towards the equator, the lower the axis points, until eventually when you reach the equator, the axis would actually be horizontal. And here at Paranal, the latitude is about 24 degrees, which is about 25 degrees different from back in England.
And I know you're planning to look through it, but you're also planning to do some imaging today. So tell us about the camera you've got to do that.
I've actually brought along 2 webcams for imaging of the planets, a black and white webcam and a colour webcam. Of course, the webcams remain the most powerful tools for high-resolution imaging of the planets. And
so I know you're looking forward, as I am, to the southern sky, but what are you going to look at first?
Well, of course, I'm completely spoilt for choice here in the southern hemisphere. I think my first object will probably be the Magellanic Clouds, as I've never seen them before.
Well, you'll have to fight me for the eyepiece, but thanks for bringing it all out.
Of course.
While Damien's imaging will focus on the planets, Daniel has other targets in mind.
We're looking at an object in Orion. It's commonly called the Waterfall. It's a very small, dim, star-forming region, and it's close to a nebula that's better known, which is called NGC 1999. It's just south of the Orion Nebula, which means up here. It's above the Orion Nebula.
So these are all part of the same star-forming complex in reality?
Yes, exactly.
And you create colour pictures in an interesting way?
Correct. We will take a sequence of probably 5 to 6 pictures in each color. That's red, green and blue. And then probably 8 to 10 pictures in luminance. That's the white light.
And then add them together in the computer.
And then in the computer everything gets mixed up together with a little bit salt and pepper, and we get a nice picture. Yeah.
Fabulous. Now you've travelled all over Chile, you've lived here, and how does this observing site compare?
We'll be able to tell tomorrow, but from the looks of it, it looks fantastic. Yeah, we are very close to the ocean. It looks like the seeing is going to be marvelous. The wind is dying down, so everything looks like it's going to be real fun tonight.
And of course, the other advantage for us of having you here is we need a local guide to the sky. I've never seen the Southern Cross, let alone the faint fuzzies, as of now. So maybe you should tell us about a few of the objects in the southern sky that we won't know about.
Sure. I mean, well, I'm Belgian myself, so I needed some time to find my way around the skies, and sometimes I'm still looking a little bit upside down to find my way. But yes, the main highlights, of course, are the Magellanic Clouds. They are deep in the south. Then we will have some other nice goodies like the 47 Tuk, which is a very nice globular cluster. We will see Omega Centauri, although it's a little bit low in the sky at this time of the year. And if we start early, we will have still a nice view of the Milky Way heading towards the west.
The Magellanic Clouds are our galaxy's most obvious neighbours. 2 small dwarf galaxies, they orbit the centre of our own Milky Way, and each time they pass through, gas and dust is being stripped from them. In fact, our galaxy is actually cannibalising them. It's 3 hours after sunset, and with the moon above the horizon, it's still one of the clearest and darkest views of the sky I've ever had. And we're using a night vision lens to try and give you a flavour of what we can see from this remarkable sight. Daniel and Damien are still hard at work setting up their telescopes and cameras, but let's interrupt and get a tour of the southern sky. So let's start with the familiar parts of the sky, but there's something very odd about Taurus.
Yes, absolutely. We're seeing it completely upside down from how we usually see it in England, and the whole perspective of the sky is completely changed and very difficult to get used to. Yeah. The very distinct Pleiades cluster is really quite stunning to see.
And there's at least 12, 13 stars visible with the naked eye in the cluster. So again, it's a really good indication of quite how good a sight this is.
Absolutely. And of course we have Orion pointing at a very odd angle toward the horizon.
Yeah, the sword's hanging upwards from the belt with the nebula, which you can see as the second star, is obvious with the naked eye. It's obvious there's something going on. Yeah. You can see the nebula.
And Sirius is also in the Canis Major there, is upside down.
Yeah, it's interesting. Sirius, the brightest star in the sky, always seems to really stand out at home through the murk and the fog. But here it's bright, but it's not noticeably bright in some of the other.
Then if we go more south, we go in the direction of the Magellanic Clouds, which of course are not visible from Europe.
I can't believe how large on the sky they are.
Yeah, they are absolutely remarkable to see for the first time.
But they're obvious with the naked eye. How do they look in binoculars and in a telescope?
Well, binoculars are fantastic for looking at these objects, and of course one object that I can't help but mention is the spectacular globular cluster 47 Tucanae, which we've enjoyed absolutely stunning views of this evening.
It's also my favorite one. The interesting thing about the Magellanic Clouds is that each one has a highlight. Close to the smaller one is 47 Tucana, just mentioned. And on the edge of the other one, of the large Magellanic Cloud, is the Tarantula Nebula, which is also a highlight in a Dobsonian or plain binoculars.
It's also where the nearest supernova to be detected in recent times went off in 1987, was in that region.
Further down to the South Pole over there, Octans.
It's remarkable with the pole quite how empty a region of sky that is. There's no bright stars there at all.
Yes, polar aligning is... we are so lucky to have Polaris in the UK, we really are.
We've also got the nearest large galaxy in the sky. On the other side, moving back round towards the north, there's Andromeda.
Yes, it's in a different perspective from in England, but the incredible dark skies here at Paranal make it such an easy object to see even with the naked eye.
I've always said that you can tell how good a sight is by counting the number of stars you can see inside the square of Pegasus, and I lost count at around 30, which I suppose answers the question. How are things going?
Fine, actually. The wind is bothering a little bit, but the seeing is good and the transparency is good.
And we just got the first image of the field.
We just got the first image of the field. I'm brightening it right here now, so we see the nebula coming through.
You can see the waterfall quite clearly.
The waterfall is coming out. We can do a quick first calibration on it.
Right.
Just...
Yeah. Oh, and you've lost all the back. Wow, that's an amazing image already.
Yes, but it's only one single frame and it's still very noisy.
Of course.
What we have to do now is collect more frames.
In different filters.
In different filters and of the same filter as well. And then we will stack those different frames and get rid of the noise.
And end up with our full colour image.
Exactly.
I have to say, I can't believe the detail on that. There's so much nebulosity
going on, right?
Absolutely.
This area here is NGC 1999. The waterfall, and this one is a nice Herbig Haro object in red. Yeah,
that's amazing. How long was this exposure?
This was 15 minutes, and so we're going to use about 20 shots.
Okay, well we should let you get on with it. Okay. Good. If I look at the small Magellanic Cloud through binoculars, it's an amazing sight, but there's a smaller patch of nebulosity just next to it. It seems very concentrated. Can't quite make out any structure in it. You got it in the telescope?
I certainly have, Chris. And this object is the globular star cluster 47 Tucanae, and the view is absolutely magnificent.
Yes, of course, the binoculars show it, but they don't show any of the individual stars. What about the telescope?
Here in the telescope, you can
Let's
actually
have a look.
you can actually see the cluster resolved into many thousands
Wow.
of individual stars.
That looks almost as if you put a photo of it on the end of the telescope. That's absolutely incredible. You can still see the very strong central cluster.
Yes, it's very concentrated towards the core.
I mean, tens of thousands of stars in this object. It's almost a mini galaxy, but because it's close enough, you can actually see the stars. And then there seem to be some lanes. If you have a look in the outer regions, where you can resolve the stars, they seem to be almost concentrated into lanes.
Absolutely, Chris. I can also see these, and they radiate out from the core of the cluster.
Yeah, it's not something I'd seen. We have a couple of bright globulars in the northern hemisphere that we can see from the UK, but nothing like the resolution of this, nothing like the size of this one. It's incredible.
It's an absolutely amazing object compared to the M13, the best globular cluster we can see from England. It really, 47 Tucanae, shines above it.
Yeah, and of course it's ideal for small telescopes because you need the field of view. A bigger telescope would magnify in and you'd miss the splendour of the whole thing. It's just incredible.
Absolutely amazing.
It's 2 a.m. and with the Southern Cross and Eta Carina rising behind me, I'm going to call it the end of a fabulous night's observing up here on the mountain and leave Daniel and Damien to get on with their hard work. I can't wait to see the results in the morning. We should have some truly stunning photographs of this beautiful sky.
Certainly, Chris was enjoying the southern sky, and most rather I wasn't there too. So now, on to the great new telescopes. Welcome back to Isabel. I'm delighted now to welcome also Dr. John Richter, the radio astronomer. We know about large telescopes, and one and more are being planned. And one of these is the OWL, overwhelmingly large telescope. And that really is going to be large, Isabel, isn't it?
It is. It's going to be very large. The proposal from the European Southern Observatory, ESO, is to build a telescope 100 metres in diameter, which is over 10 times the size of the current telescopes we have when measured in the diameter of the telescope.
It's in the planning stage now?
It is in the planning stage, and it's one of many that are being considered for future telescopes.
I remember a conversation I had many years ago with, of all people, Edwin Hubble, talking about the building of the 100-inch reflector on Mount Wilson in 1917. And Hubble said to me then the purely engineering problems were just as great as the optical problems. And with OWL, the purely engineering problems must be horrendous.
It will be a challenge, definitely. This structure will be similar in size to for example, the Jodrell Bank radio telescope, but made of glass and steel, and the whole structure, which could weigh up to 14,000 tons, has to be tipped around the sky in the same way we do with current telescopes. So it's certainly a challenge.
Of course, it's not a single mirror, is it?
No, it's not. The largest single mirrors that we can build at the moment are about 8 metres in diameter. So obviously to build a telescope up to 100 metres in size, we have to build it up from many smaller segments.
How many?
Well, there'll be over 3,000 in OWL for a 100-metre telescope.
One thing we've got to remember, I think, is that all branches of astronomy now work together. Optical astronomy and, of course, radio astronomy. And, John, great developments here. What about ALMA?
Well, indeed, Patrick, ALMA is a radio telescope which we're currently started constructing in Chile. And this telescope is being designed to answer some of the fundamental questions about origins of planets, of stars, and of galaxies in the universe. This is currently one of the very exciting topics in astrophysics. Now, the problem is that these objects will form in very cold gas clouds. If we want to look at these gas clouds, then we have to work at wavelengths which are 1,000 times longer than optical light. In other words, a wavelength of about 1 millimetre. So the Atacama Large Millimetre Array, ALMA, is a radio telescope which is designed to detect radiation with a wavelength of about 1 millimetre and make very detailed images of these gas clouds where stars, planets and galaxies form.
How many dishes involved?
Well, we are building 64 separate dishes. Each of those is a 12-metre parabolic reflector. And in total, that makes a collecting area very similar to OWL, to a 100-metre single telescope. but we move the telescopes around this very high plain in northern Chile, and we can synthesize the effect of a single dish up to 15 kilometers in diameter.
How can OWL come in this one?
Well, OWL is also an extremely powerful tool for spectroscopy because of its extremely large collecting area, and it allows you to take spectroscopy of very faint sources, for example planets orbiting around other stars, and that may allow us to look for the first signs of biospheres or atmospheres around these planets, and possibly the first signs of life.
Everything is coming together, isn't it?
Very much so, I think, yes. Increasingly, you can't use a single telescope to answer your astrophysical problem. You need to build a suite of complementary instruments and use them all to answer the scientific question you are chasing.
Isabel, John, thank you very much. So I wonder, where are we going to go? Well, one thing I'm quite sure, there are many surprises in store, and personally, I always expect the unexpected. Meanwhile, when I come back next month, we're going to talk about the Saturn probe and the exploration of Saturn's big satellite, Titan. Until then, good night.
There's an extended version of The Sky at Night when Patrick learns more about the world's largest telescope tomorrow at 8:30 over on BBC 4.